Hello, this is a video on the fourth experiment for Physics 71.1, which is about projectile motion. So in this experiment, there are only two key objectives, and this time around, as compared to the last experiment, we will be able to do both of these objectives. So in this experiment, you are expected to apply concept from two-dimensional kinematics to predict the impact point of a ball in projectile motion, as well as describe the trajectory of a ball in projectile motion. So before we discuss the experiment specifics, let's first have a short introduction on the concepts behind projectile motion. So a projectile is any object thrown with some initial velocity subject to a uniform acceleration due to gravity. So some examples of projectiles are things that you would throw up in the air, such as balls or other similar objects. So although your ball's motion might be complicated at some time, so one defining factor of objects in projectile motion is that there is an arcing motion as it flies unimpeded. So this motion is modeled using the following. So first, we assume that the motion along the perpendicular directions are independent. So this just means that we can model the x and y motion of the object up in the air separately. And two, the most significant contribution to produce the motion of the projectile is gravity. So this phrase or sentence rather is just a restating of the assumptions that are fundamental to the free fall phenomenon that we have experimented on previously. So using these two arguments together, we can come up with the following kinematic equations for the projectile motion phenomenon. So here we have these accelerations, velocities, and positions. So in particular, we have this x is equal to x naught plus v naught xt, and y is equal to y naught plus v naught yt minus 1/2 gt squared. So here, these two formulas, these are the ones that we will be using. So note that the constants here, x naught, y naught, are initial positions, v naught x and v naught y are initial velocities per component, and g is your acceleration due to gravity, which again is 9.81 meters per second squared. So note here that we have a pair of equations. So x and y both are a function of a common variable t, which is for time. But since we can treat these equations as a parametric set of equations, we can eliminate the factor t to instead have a equation entirely made up of y's and x's. So here we have our kinematic equation where our vertical position y is a function of your horizontal position x. So this formula may not be one that you will encounter in Physics 71. But if you notice here, the factors that are included in the formula are the same as the parametric equations. So you have here your v naught. So this is just an overall magnitude of the initial velocity. You have your theta as your launch angle. You still have your x and your x naught and y naught, and you still have your g. So notice here that your formula is still quadratic even though the parameter t has been eliminated. While the parameter t has now been eliminated, your formula is still quadratic in terms of x, your position. So from here, you can see, since you have a square dependence on the position, you have a trajectory that will look like a parabola, which is what we can expect for a projectile motion. So in this experiment, we will confirm this by obtaining a data set of heights for every horizontal displacements. Furthermore, we can set the initial position in the equation above and yield an equation for the effective range of the projectile, which is your equation 5. So the range of your projectile is the horizontal distance from your launch point to your landing point in your projectile. So notice here that your range is a function of your initial velocity as well as your launch angle. So now we move on to the experiment proper. So the actual experiment here will be done by using this website here. The link is given. This is actually clickable. So if you click this link, it will direct you to a specific website. So let me just minimize my screen. So when you click the link, it will take you to this website here. Upon taking you to this website, you can open the simulation by clicking play here, which will give you a loading screen as follows. So once your loading screen has now been completed, you click intro, and this will now take you to your projectile motion screen interface. So let's explore this a bit. So let's read the procedure. So upon clicking the play button, so we are redirected already. So you will be using the intro interface check. So drag the base to change the height and drag the Canon mount to change the angle. So the initial height should be set to 0. So I can click anywhere here. So I can click the Canon itself or its platform to change its height. So we will be changing this height to 0. So we'll drag this all the way down. And then we can drag the Canon mouse. So I will be clicking and holding my mouse to change the angle. So I can click this button here, this red button, to shoot a projectile. And I can click the eraser button to remove all my trials. So let's move next. So now we have all our other tools that we will be using. So we have our crosshair tool. So from this top right screen, we click and drag the crosshair tool. So this will only work for defined points in the trajectory. So next, we also do the same for our tape measure. So the tape measure measures points that are between your plus and minus. Your plus and plus, rather. Sorry. There are 2 plus points here. Let me just zoom in. So here you have 2 plus points from the label of the tape measure itself up to your arbitrary measuring point. So to measure distances, you simply drag your tape measure and it will give you a finite distance that you can use for your measurements. So if you want to return your tools, you can simply just put them back in this box and they will return here and their settings will actually reset. So next, these screens here will allow you to choose your projectile type. So you can choose the object with which you are firing. So you can choose any object of your choosing. So you have your golf ball, tank shell, even a human, a piano, and a car. So this is what your human would look like. This is what your tank shell would look like. So now that I have fired, by the way, so I'll go back to my crosshair tool. So the crosshair tool works for defined points on the path. So the defined points are defined by these little dots on the projectile trajectory. So if I put my crosshair on the path, nothing happens. But if I go to the defined point, I have a measurement of time, range, and height. Again, range is your X component, while your height is your Y component. And lastly, you can simulate the effects of air resistance if you check this box out. We also have a real-time realization or visualization of velocity and acceleration vectors. So if I fire my projectile with these arrows checked, what I will get is a real-time motion of my vectors. We will not be using this tool for this experiment, but it is nice to know. So now let's go on to our experiment proper. So part 1 would be measuring the range of projectiles. So the instructions are to set the initial velocity to 0 and initial height to 0. So we already did the initial height. We want to set the initial velocity, so we click here Or alternatively, we can drag this bar here to set the initial velocity. So we can again drag the Canon mouse to change my angle. And we can launch the projectiles and measure ranges for all angle values in the table. So for example, I want to fire at a 25-degree angle. And I want to measure my range. I take my tape measure. I put the plus sign here where the Canon is starting its projectile path. And then drag my tape measure to the landing point of my projectile. So in this case, I measured 7.79 meters. So this will be my range measurement. So in part 1, we will be repeating steps 1 to 4 for different initial velocities of 15 meters per second and 20 meters per second. So now let's move on to part 2. So part 2, we will be determining the height of a projectile for varying horizontal distances. So we select a launch angle among those used in part 1, then adjust the angle of the Canon to this value. So we launch the ball by clicking the shoot button, and we drag the time range height crosshairs to any point along the trajectory to measure the range and height at that point. So basically, we will see this more clearly in the data sheet section. And we will do the same for different initial velocities again, just like with the previous part. So lastly, we will be using data analysis. We will be graphing the data you will be obtaining, and we will be using our spreadsheet programs to do this. So similar to the last experiment, you will be checking for all the elements of the graph to complete them. Your grade here will be also dependent on how many chart elements or graph elements that you are including. So note here that you will be using Microsoft Excel or any spreadsheet software to add a best fit line and R-squared value to your plots. So note here that I will not be going through the specifics of how your plots are generated again. But if you have somehow forgotten or you do not know, you can refer to our video on the third experiment. So now let's move on to our last section, which is your data sheet. So part 1 of the experimental procedure will be filled out in table 1. So you have here a measurement of different ranges for different angles and different initial velocities. So you just record the measurement of each range that you have for each condition here. So similarly here, for the trajectory of a projectile, you will be measuring different X and Y values for a selected angle here of your choosing. So for example, you can choose 45 degrees, 60 degrees, 75 degrees. It does not matter. Just choose one and stick with it for all your measurements. And also note in your data sheet which angle you would choose. So as an example, I can get rid of this for now and the erase tool. So if I want to measure my X and Y values, I will fire my projectile. Okay, let's make it a little farther. All right. So for each point on the crosshair, I can select my range and height. So range again is X and height is Y. So I can log these 1.7, 1.65, for example. So these values are changing for each dot. So you can choose 6 random points to model your parabola. So here you don't have to choose the first 6 points, although that is also a valid assumption. But as much as possible, maybe try to at least cover the entire trajectory. So we have here our figures. So what you will be plotting in particular is your plot of your range versus sine 2 theta for all your trials. So this is your data from table W1. So just like with the last experiment, I want you to superimpose all the data points you have on a single graph. So I will expect more than one data trend for each figure here. So on your figure 2, you have your plot of y versus x. Now this is data you obtained from your table W2. And again, overlay all of your data on one graph. So just like with the free fall experiment, I will be expecting you to not connect your data points and also to include a trend line of the appropriate shape as well as an R-squared value for us to check the goodness of fit. All right. So now lastly, we move on to our questions. So I'll maximize my manual again. So we have here 3 questions. All right. So first question, are your graphs consistent with the expected behavior based on equations 4 and 5? So just as I recall, your equations 4 and 5 are your y of x and as well your range. So from here, the question is basically asking, is the trend that you find in your figures the same as that presented in equations 4 and 5? So are they consistent? So number 2, what assumptions must be made in equations 4 and 5? So just as a hint, I will give you, these are general assumptions that you can make when using projectile motion. So this is more on the theoretical side. So if you are lacking information here, you may refer to your Physics 71 lecture slides. And lastly, try turning on air resistance. What are the effects on the range and final height of your projectile? So note here that this is a correction actually. This is not your final height, but rather this is your maximum height. Of course, your final height will always be 0 since it will always land on the floor. So note here that you are dealing with maximum height. So here, I'm not expecting any numerical values or plots or anything like that. I am just expecting you to write your answer in sentence form. Okay, so that concludes our discussion for the 4th experiment. Thank you for watching and good luck.